I imagine that in your second year you covered the bearing capacity of foundations and you probably came across bearing capacity factors. And I guess you had no idea where these things were coming from. You just got numbers, 9 for a deep circular foundation, 5.14 for a strip foundation. These funny numbers, and where the hell did they come from? Um, Now, we need to do better than that. And as good engineers from a good engineering course, you need to really understand how do you get these things? And that's what we're going to do in the next series of lectures. We're going to cover what are called bound solutions. Those are upper bounds and lower bounds. The upper bounds, which we'll start with, those are the easy ones. And what you really have to do is to think of a mechanism. And largely the most difficult bit is the sort of limitation of our imagination in thinking of a possible mechanism of collapse. How can something collapse? We'll confine our lectures to foundations because they're the easy ones, but you can apply these methods to anything, to slopes, retaining walls, anything you like. They're universal methods. They're very fundamental. You will have come across in slopes and retaining walls another type of method called limit equilibrium, which engineers in practice, they love that. They're horrid. And what I'm going to show you, these bound solutions are much more elegant, much more fundamental, and much more correct. You're going to do hand calculations with me. Of course, you're never going to do that in industry. Nobody would do that. There are computer programs you simply buy that do these things for you. But you, as good engineers, you need to know how the methods work so you understand their limitations. Of course you do. Okay, so having said all that, we're going to start with upper bounds, which are the easy ones. Lower bounds get seriously nasty. We're also going to stick to foundations, I said, and also undrained loading only, because drain loading is really at the MSc level. It gets very nasty. The equations get very long. So undrained loading of strip foundations only. Okay. When we're calculating failure loads for a structure, we often assume some sort of mechanism like this, which we'll talk about in this lecture. When we assume a mechanism like that, we're assuming that the soil behavior in stress strain is rigid and then perfectly plastic. So we're ignoring all of this nonlinearity of behavior. So what we're assuming is that the soil in the blocks is simply rigid, and on the failure planes like this or like this, it's reached failure, so it's failing along here, perfectly plastic. Question is, of course, which strength do we use? Is it the drain strength, the undrained strength? Here we've just got a critical state, but you might have a peak. Do you use a peak strength? Who knows? They're your choices. Contrast that with settlement calculations that you will have done in year 2, I guess. When you calculate settlement rho, you're going to need some sort of stiffness. So compare that with the assumption for settlements. Now, which stiffness do you choose? This is nonlinear. It's crazy. You might take that initial stiffness, but it could be that one, or it could be that one. I mean, any of these lines could represent that curve equally well. But nevertheless, as an engineer, you've got to choose one, and of course, it's crazy. These are typical problems that we encounter in geotechnical engineering. So we might have a foundation with a settlement, and if we plotted the settlement against the stress on the foundation, Q, with a force over the area, it might in reality look something like this. It's a bit difficult to decide when a foundation fails sometimes, because as you keep increasing the settlement, the load keeps increasing. So generally we define failure as the start of excessive settlement, which is maybe about there. Of course, a slope, it's much easier to know when a slope is failing because it's in your face, and it's pretty catastrophic. So you can calculate, and you've already done this, some sort of inclination and height of the slope that will cause failure. You know about retaining walls also, a typical other engineering problem. If the retaining wall moves outwards, you get active pressures. If it moves inwards, you get passive pressures. And This changes the stress distributions around the wall in that sort of a way with the movement, but you know all about that. What we're going to think about now is that we might have solutions for each of these structures in terms of limit states, that means collapse, or serviceability. We're only going to look at collapse or limit states here in these lectures. We will not deal with serviceability. We can have solutions for undrained loading. Of course, undrained loading is always followed by a consolidation as the pore pressures dissipate, but we will only deal with the undrained part. And you could have solutions for drained loading. We're only going to do undrained because the drained is very difficult. Whatever solution we have, whatever method we employ, you should really be satisfied three things in life. Firstly, equilibrium. Secondly, compatibility. And thirdly, you must consider the material behavior and get that right. Now, you do know something about equilibrium already. You will, in limit equilibrium, have considered balancing the forces must balance. So the sum of the forces in any direction must be zero, or the moments must add up to zero. You've done that, resolving forces or taking moments. So you might do that with a force polygon. I don't know if that's what you did, but let's consider this retaining wall. It's got a foundation on top of it. The retaining wall, I'm going to do the active case, so that's an active force. We're going to do drained loading only in this little example. There's a slip or failure plane that we are postulating. So it's active, so the shear stress here on the failure plane is going that way. Don't forget, if you want passive, you've got to reverse that one. And this is a normal force on the shear plane, a normal force. These are forces, not stresses. So the normal force would be something to do with the stress multiplied by the length or integrated over the length. W is the self-weight of this block of soil. One thing I forgot to mention is that we've assumed in this little example no friction on the back of the wall. So for a force polygon, you may remember we draw a vector for each force in the same direction as the force with the length proportional to the force. Well, let's start with what we know. We know Q, the foundation load, and we can draw a vector. And we can make that length proportional to the length of the vector. So if that's 10 kilonewtons or something, you can make that 10 centimeters, whatever. You just make it proportional. Then you know that the self-weight of the block here, the block that's failing, must act vertically. It's gravity, so that's W, and you know the weight of that block. You can calculate it. So we can continue our polygon. Now we're in trouble. We actually don't know the normal force or the shear force. So we're in trouble. What we do know is the direction of the normal force. So we can draw a dotted line up here. We also know the direction of the active force, PA. It's horizontal. And that's horizontal because there is no friction on the back of the wall. So that's horizontal. And then you know that if the soil is failing, the shear force must be the normal force multiplied by tan phi dash, the friction angle of the soil. So you know that T must be at right angles to N and must be N tan phi dash. So it must fit in like this, and therefore that must be the active force because the force polygon must close. And hence we've calculated the active force. That was very simple. That was just for limit equilibrium. But we're going to see something much more sophisticated when we get to lower bounds in the next bit of the lecture. Not right now. We're going to do something much more rigorous in lower bounds. We're not going to just consider the global equilibrium of forces. This is resolving, as you say, in the large. We're going to consider the stresses at each point in the soil and consider whether they are permissible, whether they are allowable or not. That's much more sophisticated. Now we turn to compatibility. Compatibility means that displacements must balance, just like force is balanced in you were resolving forces a moment ago. It means that no holes must appear in the soil, and no soil must be eaten up or disappear. Now we're going to deal with a rigid block here, rigid blocks or wedges of soil, and slip planes in between. So this rigid block is going to move down on a slip plane here, while this block is going to move up on a slip plane here. And then, of course, there will be relative movement between the two. O represents all the stationary soil outside that's going nowhere and is also rigid. F represents the foundation and the movement of the foundation, and I will only consider that the foundation is going to move vertically. So if you like, there will be a relative movement between the foundation and block A that's going off this way. Now for rigid bodies, and this will only work for rigid bodies, we can draw a displacement diagram, and that must close. So we're going to draw vector lengths that are proportional to the various displacements of the blocks. So the length of each vector will be proportional to the displacement. So let us start just by defining that the foundation is going to move down by this much. You could make that 1, for example. Call it what you want. Relative to the vertical movement of the foundation that we are assuming, block A will move down on this slip plane, which transferred to be exactly the same angle here. And of course, block A can only have the same vertical displacement as the foundation, otherwise they would lose contact or the foundation would disappear into block A. And these are rigid blocks, so they can't. And that displacement is delta AO. Block B has to go up on this slip plane, this failure plane, with the vector delta BO. Of course, the length of these vectors are defined by this construction. We didn't know delta AO until we decided it has to go the same vertical distances as F. Similarly, we don't know delta BO until we realize that the vector delta AB, that vertical one there, has to be vertical because it's the relative displacement of block A relative to B, which is downwards. Or, if you prefer, the relative displacement of block B relative to A, which is vertical. So on here, B is above A, and it's vertically above A. So it's this construction that allows us to define all of the lengths. So in upper bounds, the consideration of compatibility is rigorous in this way. When you did limit equilibrium, you didn't consider any of this compatibility. You just chose a mechanism that was a mechanism. In some way, that is thinking about compatibility, but not very much. This is rigorous. So we will be drawing plenty of displacement diagrams. Some people call these velocity diagrams. The third thing we need to consider is the material properties. The stresses and strains in the material should be correctly related by strength and stiffness, and its constitutive equations that relate equilibrium stresses with the compatible strains. Now we've had 3 things to satisfy. Of course, you're never going to get a solution that satisfies all 3 things for real problems because, firstly, the material behavior is very complicated. You know how hideously complicated soil behavior is. So you get complicated constitutive equations. Those are the equations defining the stress-strain behavior. The engineering problems have got complex geometry. That means what's called the boundary conditions. And then there are self-weight effects on the structures sometimes. So all of this complicates the solution no end. So we use simplified analyses or bounds. So for a foundation, if I push my foundation into the ground, I might get some sort of load deflection curve like this. And we want to find some sort of failure stress like this, or failure load somewhere in that region. We will calculate a safe lower bound, an answer that we know is safe and we know is below the true answer. And we will calculate an upper bound that we know is unsafe. Now that may seem a bit useless to calculate an upper bound that you know is unsafe, but of course what we will be doing is to try to minimize the upper bound and maximize the lower bound so that we make as narrow as possible the gap between the two so we can be pretty sure about what the number should be. Now, let's talk about the difficulty of the different types of bound solution. Firstly, we're going to deal with undrained upper bounds, and those are already going to be pretty difficult. We will also do undrained lower bounds, which generally people find very difficult. We will not do drained upper bounds because they're really nasty, and there are no words to describe drained lower bounds. We just pass on. We're not going to do those. Do an MSc if you want to do those. So take year 4 option if you want to do more of this. So we're going to start with upper bound solutions. First thing you've got to do is assume a compatible mechanism of plastic collapse. This is the formal statement of the problem. For an increment of displacement, if the increment of work done by the external loads equals the increment of work done by the internal stresses due to plastic strains, then the structure must collapse. It is therefore an upper bound and must be an unsafe load. Put simply, if the soil can find a mechanism, it will. As an engineer, you cannot hide a mechanism of failure from the soil. It'll find it. In this method, the upper bound method, there is no statement about equilibrium. We don't consider equilibrium. The whole thing may not be an equilibrium. We don't care. The only thing we really care about is compatibility, and we will spend all our time with a rigorous check on compatibility. We will be doing calculations of work done by the plastic strains, so we are considering the material properties, if only in a simplistic sort of way. We're going to start with, or we're going to confine ourselves, in fact, to a surface strip foundation, undrained, remember. We need to think about the work done by the external forces and stresses, and there can be 3 lots of those. Firstly, there may be a foundation force. And to get a work done, we need a force multiplied by the displacement. And here I'm calling my displacements delta W. So delta WF for force. Then there are stresses. Might not be a force, might be a stress. And I might have a delta WQ, Q for stress. And then the block, these rigid blocks may be moving around, and then maybe a self-weight of the soil block. Self-weight might be W, and I've got a delta W gamma, gamma for self-weight. So for undrained loading, the work done by all these external forces would, E is the external work done. So delta E, the increment, would be the summation of the foundation force multiplied by delta WF. The stress needs to be multiplied by an area, and then by the distance that the stress moves. Don't forget in the area that we only really need the width, because we're multiplying by 1 into the diagram. And for the self-weight, it's going to be the unit weight gamma multiplied by the volume of soil, the volume of this block. And we only use, of course, the displacement in the direction of the force. So we only want, although the block's moving diagonally, we only want the vertical component because the force is vertical. I won't go through it, but if you were to go to drain loading, then the water in the soil remains stationary while the soil particles move around it. So the water does no work. We won't do this, but just for your interest, the force element part of the summation remains the same. But when you consider stresses, you need to subtract pore pressure, and when you consider the unit weight, you have to subtract the unit weight of the water, because as the block moves, the water remains stationary. We're going to use displacement diagrams to calculate all these displacements. And do remember that in each case, you need the displacement in the direction of the force. So upper bounds for an undrained strip foundation. You, in year 2, I suppose, must have learned all about bearing capacity equations when you saw many rather boring tables and graphs which you use to calculate bearing capacities of foundations. But how on earth did anybody ever get them? One way to get these things is from bound solutions. One way. There are other ways. So you will have come across an equation like that. The undrained bearing capacity Q is NC, an undrained bearing capacity factor, multiplied by SU, the undrained shear strength. I'm sure you've seen that. And you've almost certainly seen this diagram. This is from my old colleague at Imperial College, Alex Scampton. NC, the bearing capacity factor, plotted against depth to breadth ratio. We're going to spend an awful long time now just looking at how to get one of these numbers. This is for a strip foundation at 0 depth. So d over b is 0. So, and you notice the solution is 2 plus pi. That's 5.14. Keep that in your mind. So we're going to start with undrained upper bound solution for a surface strip footing. Remember, all the calculations are for 1 meter into the diagrams, 1 meter into the screen. We're going to be able to neglect self-weight, the weight of the soil blocks moving around, because you'll see quite quickly that there's as much soil moving down as soil moving up for a foundation on level ground. That's not true if you've got a foundation on a slope or something like that. And there's one of the examples in the tutorial where the foundation's on a slope, I believe. So it's not true anymore. And you will need to take account of the self-weight of the soil. Generally, we don't. For undrained loading on a flat slip plane, a flat failure plane, the shear force on the slip plane would be the shear stress multiplied by the length of the plane. But if it's failing, then the shear stress would be the undrained shear strength. So we get the shear force is the length multiplied by the strength. And the internal work done, we just got to multiply by the displacement, delta. So the internal work done, or energy dissipated, would be the length, strength, displacement. Keep that in your mind, length, strength, displacement. So here we go with the first example of how to do it. We're going to try the simplest possible mechanism, 2 45-degree wedges or triangles. And this block here is going to slide down on a 45-degree failure surface, while this one slides up on a 45-degree failure surface, and there'll be relative movement between blocks A and B there. O is a stationary soil. P is a stress applied to the foundation over a width B. Displacement or velocity diagram. If you're really smart, you can call them Hodbo graphs. Always start with your fixed point, which is O, stationary soil, which is stationary, so it's fixed, it's a point. Remember, we're only interested in the vertical displacement of the foundation, so this stress P is moving down. Now, I can call that displacement what I want. I've called it delta V, I could call it 1, I could call it 10, I could call it Matthew. It doesn't matter. It's the relative displacements of everything that will turn out to be important, not what you call it. So I'm going to call it delta V, but that delta V will disappear very shortly. A is moving down on this 45 degrees slip plane relative to the stationary soil. So from the stationary soil O, you draw a 45-degree line downwards. And of course, remember, it must stop at the same vertical displacement as the foundation P. Otherwise, you're going to get a gap opening up or some soil disappearing or something. And that angle there is 45 degrees. B is going to go up at 45 degrees. And you can see we don't really know how far to draw this, but remember that B's got to be vertically above A, because that relative displacement there on that vertical slip plane must be vertical. So there is B vertically above A, and if that's delta V, this will be root 2 delta V, and this will be 2 delta V, and that again is root 2 delta V. And that's a right angle in there corresponding to that right angle. Notice how the velocity diagram has got all the sort of same angles as the mechanism. Well, it doesn't quite look like the mechanism, but it's got all the same angles in it. Now, I do beg you, when you solve these things, please draw a table, especially in your exam answers, because it enables me to see where you've gone wrong. And you know, as an examiner, you're trying to give as many marks as possible. So a table is always helpful. So we've got three slip planes, AO, BO, and AB. We need the length of the slip plane. Well, if that's B, that's √2 delta B, and so forth. And we want the displacement of each slip plane. Well, if that's delta V, that's √2 delta V, and so forth. And then we take the length multiplied by the strength, SU, multiplied by the displacement for each one, length, strength, displacement. And then we make a summation, we get 6B delta V SU. We also need the external work done by the stress P, that's E. External work done is P multiplied by B to get a force, multiplied by 1 into the page, and multiplied by the displacement of P is simply delta V. So PB delta V. So now we've got to equate E and W, and we get 6 SU as being the stress on the foundation. Now, we were after 5.14, so even with an idiotic mechanism, we're not so far off. As we said, as this block moves down, that block moves up, so we don't need to worry about the self-weight, because the work done by this self-weight would be cancelled out by the work done by that self-weight, because it's on level ground. Remember, for the tutorial example, that will not be true if the ground is not level. Let's think about our mechanism. Well, that's the one we just did. It's the simplest possible one for an upper bound. I don't know if I can think of a simpler one. And so we wouldn't expect the answer to be too close to the optimum. And actually, we're not so far off. We're kind of like this. That's going to be 5.14 SU. We know what we're looking for. We're already at 6. You know, we're 20% off or less with an idiotic method. Well, actually, that's actually showing you how sophisticated the method is. That even if you use it with a poor choice of mechanism, it still gives you a very good answer. How close we can get our unsafe upper bound to the real answer will depend on how clever we are with our mechanism. Of course, in reality, and you'll see this in one of my tutorials, we can use model testing with centrifuges to try to get the correct mechanism. Well, what type of mechanisms can you have? Well, if you had something like a retaining wall, you might have a simple plane, a plane failure like that. You could have circles or arcs, which we'll look at. These are wedges or triangles that we've been doing. We've done 2, we'll do 3 in a minute. And don't forget, everything is 1 meter thick into the screen. In upper bounds, these lines represent actual failure lines, lines of failure or slip. So you can call them failure planes or shear planes if you like. That soil is actually failing and everything else is rigid. Don't worry about the corner. I know I said this block's rigid and you might think that, that corner is an issue sort of going into there, but don't worry about that. Remember, the displacements in reality are infinitesimal. So in your imagination, what you can do is just assume a little hole there to take away the worry of the corners clashing into each other. Don't worry about corners, that's not an issue. We will come across fan zones, and fan zones are difficult to get your minds around, but with fan zones, it's a circular arc here, so the soil's going to slip round on that circular arc, but then there are an infinite number of slip planes in that arc, and the relative movement of that little wedge relative to that little wedge is vertical on this radius. Now, even if there are an infinite number of these radii in a fan zone, each little infinitesimal block is still considered to be rigid. But because there are an infinite number of them, the displacement through here is continuous because they are infinite. So we're going to try some more mechanisms. What you're trying to do in using different mechanisms is trying to maximize the work done by the external loads and minimize the work done by shearing of the soil, the energy dissipation, W. That's your aim in life. So let's try 3 60-degree wedges like this. So here we have the same foundation, P the stress, B the breadth, and 60-degree equilateral triangles or wedges, O the stationary soil. First thing, displacement or velocity diagram. O is your fixed point representing all this soil out here that's not moving and is a point. P is moving downwards relative to the fixed soil, so P relative to the stationary stuff is moving down, and you can define how far that moves. I'm not going to call that delta V for a reason that you'll see shortly. I'm going to call the displacement of A relative to O delta V. So block A moves down on an angle at 60 degrees there. So that's 60. And I'm going to call that delta V. It'll be more convenient for the maths. Remember that A cannot move vertically any different distance to P. Must be horizontal there. They've got to have the same vertical displacement because you can't get a gap or beneath the foundation, and you can lose no soil there either. B has to move horizontally relative to O. So it's got to go that way. Of course, you don't quite know yet how far it's going to go, but you'll see in the construction, because A relative to B must be at 60 degrees, because as A goes down that way, B goes down that way, so B relative to A must be going up that way, or A relative to B is going down that way. Otherwise, you get a hole developing. So B relative to A is going up at 60 degrees, and so, of course, they must join for compatibility. So that's how we know where to stop the line for B that otherwise would have continued over here. They must join there. Then we know that C, relative to the stationary soil, must be going up in this direction, relative to the stationary soil. So relative to stationary soil O, draw a line up that way at 60 degrees. Again, you don't really know how far to go, but you do know that B relative to C is that line there, so it must be coming in here somewhere, and they must join. So there it is. B relative to C, well, B would be going down that way relative to C going up that way on this failure plane, and you transfer that angle onto here and almost join. This, you see, all 60 degrees, equilateral triangles here, just like there. It's not very well drawn, actually, is it? So if that's delta V, this will be root 3 over 2 delta V. And all those angles are 60, apart from that one there, that's 30. External work done is P multiplied by B the breadth, multiplied by the vertical displacement. A table again, please. One row for each slip plane. AO is that one. BO, CB, AB, and CO. They've all got the same length, B. They've all got the same displacement, delta V, from this diagram. So length, strength, SU, displacement. So it's the 5 of them, so it comes to be 5B delta V SU. Got to equate that with that. 5.77 SU. It's getting better, isn't it? Come down from 6, so we're going in the right direction. Notice more wedges, more triangles, better answer. So we went from 2 wedges, giving us, I think it was 6, wasn't it? And now 3 gives us 5.77. So how many wedges do we need? You're probably getting the idea. It's going to be infinite, isn't it? So this is better upper bound, sorry, because we're going in the right direction. We're getting a lower answer. So we're going to try now a circular mechanism, which is quite a simple one. The maths is a little bit more tricky, maybe. So here's our circular mechanism, O stationary soil, there's the circle. And we're going to allow that circle to rotate by an angle delta theta. R is the radius from the center there. The external work done, where we have to integrate from the center to the perimeter of P, the stress, multiplied by dr, R, the radius, delta theta, the angle of rotation, we get PB squared over 2 delta theta. The internal work dissipated, W on that circular failure plane, is pi b, the length, the strength SU, and the displacement, which is b, the breadth, or the radius, multiplied by delta theta. And that gives you 6.28, which is disappointing. It's got worse. Why has it got worse? It's because we've got a big failure mechanism going deep into the soil, dissipating a lot of energy, and that's not going to give us a good answer. So let's try an arc, so a circle with the center above the surface of the soil. Now I won't go through the maths in great detail here, but R, the radius there will be B over sine alpha. The rotation again is delta theta. The external work done is exactly the same. The internal work dissipated is a bit different. That's the length of the plane, the blue bit, which is that bit there. And the displacement along the plane has also changed. Anyway, this all gives you 5.52, which has got better. That's certainly better than a circle, which was catastrophic. It's also better than the 360-degree wedges, which was 5.77, so we're going in the right direction. That's already better. It might be tempting to think that you could combine a sort of a mechanism of wedges with an arc in this sort of thing. So maybe in this case, two 45-degree triangles and a sort of a thing with an arc in it in the middle like this. So A goes down, B moves across, it's not going to work. And you see it's not going to work because if you try to move them, well, A will move down, but as B moves across, you're going to get a big hole in here and some soil eaten up here, and C moves up there, but it's not compatible. You can see that. Or if you try to move it like this, you'll get some holes here and some soil lost there. And, if you try to rotate B, it's not compatible. So you would get a very low answer if you did that. I think you'd even get less than 5.14 SU, but of course it's wrong. It's not legal, and the low answer is unreliable because you're using a mechanism that is not compatible. So what you have to do is to split up this central wedge with an arc on it into infinite little tiny wedges and allow each of these little tiny ones to move vertically relative to each other on these little spokes, like spokes of a bicycle wheel. These little radial shear planes. So that little wedge will move relative to that one, relative to that one. That would move down and that one would move up relative to each other. So we're getting a continuous movement through here because there are an infinite number of these. So we're getting rotation here and vertical movements on all of these little radii as we go through here. So they all shuffle round like a stack of books. And these two are rigid. Of course, everything in here is rigid. It's just that each of these little wedges is infinitely small and rigid. So we use an infinite number of wedges sliding relative to each other in a circular motion. This is called a fan zone, like a lady's fan that she would use to cool her face. This is compatible. It dissipates more energy than this thing here, but it is legal. We need to think about the work done, the energy dissipated inside the fan zone, in an undrained fan zone. So here I've got an infinite number of little wedges, 3 in this case is close to infinity. Delta V is the displacement going in here, so the arc is moving around delta V. The size of each wedge is R delta theta, where delta theta, of course, will be infinitesimally small, and theta is the angle of the whole fan zone, radius R. On the arc around here, the work dissipated will be the summation of RD delta theta. That's the length of the plane, SU, length, strength, displacement. Displacement is delta V. You'll have to take my word for it, but the movement on this radial slip plane, so So this is moving down as that one's moving up as we rotate round. That relative movement there is delta v delta theta. The maths to prove that a student once asked me to do, and I couldn't do it, so I asked my wife, and it's a couple of pages long. So, but anyway, so take my word for it. That's what it is. So for the wedges, the work dissipated is the length r, strength SU, delta v delta theta. That's the displacement. So this is, if you like, a large length, small displacement, whereas this one is small length and large displacement. Anyway, notice that these two are the same, so you get 2r SU delta v theta. Theta, remember, is the included angle of the whole fan zone. So here we are with our mechanism. 2 rigid blocks, 1 fan zone B. Rigid blocks are 90-degree angles and 45 to the horizontal. And that's the fan zone running continuously from one rigid block to the next. The displacement diagram. Well, P, the foundation stress, is moving vertically downwards as always. A moves 45 degrees along that slip plane as always. It can only move the same vertical distance as P, as we keep saying. C moves 45 degrees upwards on that slip plane. There. The fan zone, just like it's got an infinite number of radii here, the fan zone is a circle on the displacement diagram with an infinite number of radii, just the same. Same geometry appearing here as here. So, equating the external work done with the internal work dissipated, the external work done is P multiplied by B, multiplied by 1 into the screen, that's the force, multiplied by the displacement. Now, that's delta V, and that's delta V. All of these are delta V in here. This is the vertical displacement of the foundation is delta V over root 2, which is there. Block A, we have the length is V over root 2, the strength, SU, and the displacement, delta V. Length, strength, displacement. Block C will be the same. The length is V over root 2, multiplied by strength, multiplied by the displacement, delta V. The fan zone, remember from the equation for the fan zone, we have 2 times the radius of the fan zone, that's that radius there, which is V over root 2 again, multiplied by the strength, multiplied by the displacement, and the displacement is delta V at pi over root 2. So, notice that all of this adds up to 2 plus pi, 5.14, and there we have the exact solution coming at it from an upper bound. But remember, this is only an upper bound. Now we have to do it for a lower bound.